Now, he had some medical issues, and for that reason, he asked to still give his lecture, but do it remotely. So he will be giving his lecture via Zoom. Giovanni, your presentation currently is no longer in presentation mode.
Yes, I was checking because you asked me to record it. So bye everybody. So I'm going to go into projection mode.
Okay.
So I just have to move this a bit. Projection mode now, no?
Yes.
Great. So thank you everybody for your interest. I'm honored to give this lecture. So I'm sorry I cannot be there, but so I will be talking about the type of work that we have been doing on trying to use machine learning, artificial intelligence in space science. And I am sure you know already, I mean, nobody around the planet right now doesn't know much about machine learning. I can see in every news every day. So, but it's sometimes important to recognize the difference between the different words. So what you typically hear on TV for things like a Tesla car or ChatGPT and so forth, you are talking about deep learning, which is only one of the applications of neural networks. There are other neural networks other than the deep learning. And then machine learning is a wider topic than just neural networks. Neural networks are one type of machine learning that has become very important now, and it's not new. The neural networks have been around for a long time, but the computers have become fast enough to make it work. That's the great progress of the last years. It's hardware more than software. Then, of course, big development went into making the software efficient and easier to use. But the method in itself, the idea is after the war, or even before World War II. Just the computers weren't fast enough to do this practically. But machine learning are many other things beyond neural networks that are very useful in space science, especially the clustering techniques and techniques that are for unsupervised learning. Many of them are not based on neural networks. So that's to keep in mind that we don't want to limit ourselves to the neural networks. Then artificial intelligence is actually a larger word that encompasses all that I've said so far, plus other techniques that are not based on machine learning. But, you know, for example, you can prescribe some behavior that resembles intelligence. So there are other ways that were popular until 20 or so years ago. They attempted to do artificial intelligence in other ways that were not the machine learning itself. It's probably a bit now surpassed in the sense that you want the machine to be like a child and learn from experience, but there are other ways to do artificial intelligence. So let's keep all that in mind, that you don't want to think AI and machine learning are deep learning. There are other techniques, and in fact today I will mostly talk about other techniques. So then there is a big distinction then not only between artificial intelligence and machine learning and deep learning, but also between supervised and unsupervised. In many of the recent applications that have achieved a lot of fame, like ChatGPT and so forth, recognize of images, like in a Tesla car, and that's supervised learning. So you prepare a training set and the machine learns from the training set. So it can distinguish features. For example, that's for the cars classical, that you recognize all the items that the camera sees on the video. And it is since 2016 that artificial intelligence is better than humans at recognizing images. So distinguishing features in images. So it is now used in every field, you know, from the military to the transportation to dubious government tools that recognize people as they walk around. So those things are now superior to humans. And that's remarkable because up until 20 years ago, it was always said that the hardest thing for a computer was to recognize features, that you had to employ armies of people, like at the CIA, to go through the images and recognize whether a certain terrorist was in a picture. Now machines can do that, and they do it better than humans. So that's remarkable. Then the other thing instead that is a classic example of unsupervised is clustering. You know, you prescribe this is still called machine learning. So the machine learns because it's not a prescribed algorithm, it's an iterative algorithm. So in the sense of that, it's learning because it goes through iterations based on what you give it, and it iterates until it finds the best clustering that it thinks. And there are many methods. This is from scikit-learn, which is one of the most used clustering tools in Python. And you see there are different clustering approaches, how they work in different situations. So if you have a galaxy or you have a cluster of stars, or if you have a cluster of particles, for example, in a distribution function measured from a spacecraft in situ, you can use, depending on the type of distribution that you have, you can see that certain methods are better than others in certain configuration. And then you can also see in this slide the cost, you know, that some methods are faster than others. So if you have to do millions of images per hour or more, like for example, MMS measures a distribution function every 30 milliseconds. So if you have to do this every 30 milliseconds, and you see that some of the techniques that are 12 seconds, then it certainly cannot be done in real time. So you have to consider the cost of these clustering techniques. These are two examples of supervised and unsupervised. Then the other thing that is creating a lot of attention is the deep fake, for example, and other applications like that generate false images. And you can have the president of the United States say something he would never say. And so these are examples of these generative neural networks. It's a specific class of deep neural networks that generate new images or new voice traces or anything, or new text, like ChatGPT creates a text or pictures and so forth, that based on these various techniques that have been developed. These are applications in astrophysics. For example, they have methods to generate images of type of galaxies based on these techniques. But it can also be used to replace physics-based modeling. So you can have these generative neural networks in various types that there exist. For example, the graph neural networks or the generative adversarial networks there, where you put two networks to play against each other. One generates fake images and the other one tries to recognize them to be fake. And then, at some point you train them so well that the generative network becomes so good at generating images that it starts to distinguish the real from the false. And so there are many of these techniques. And then other techniques, surrogate models. Surrogate models basically replace an algorithm with a simpler neural network or other techniques of machine learning to give you the best guess of what would be the answer if you were to run a simulation. Those are very interesting techniques that are in between physics based modeling and machine learning, where the machine gathers information from the simulations. You do many simulations and then train the neural networks to replace them. Or you can also include the physics constraints in neural networks. So those are the physics-informed neural networks. These are neural networks that, maybe it's in the next slide, indeed. The physics-informed neural network, you insert into the neural network a constraint that when it minimizes a neural network essentially is minimizing some complex formulas that describe the nodes of the network. And then there is a minimization techniques that tries to get the best answer by reducing a certain target function. And you include in this procedure some physics equation that must be satisfied. For example, the divergence of B must be 0, or the energy should be conserved. Stuff like that you can include into the training of the neural network. And then one of the most recent applications is that you use machine learning techniques, not necessarily neural networks, typically it's other techniques, to actually learn the physics. Is like a scientist, like you were Ampere, and you were trying to discover the Ampere's law by doing experiments. So you let the technique take the input and the output, and you give it many possible equations it may use, and the method will automatically try to formulate the equation that best describes the physics. So at this point, once this works, we can all lose our job and go to the beach or something, provided the government gives us some salary for doing nothing, since the machine are doing everything for us. But so far has not yet been, let's say, used extensively to replace humans. We still have our jobs, and we still want to discover the equations the old-fashioned way. But the machines are in the process of being able to, given the input and the output, that can be simulations, but it can also be observational data. You feed them the data, there is some output, like for example, you want to discover, let's say, for example, the equation of state. And then you have to express the pressure in terms of the density and the temperature. And the machine can learn for a certain type of configuration, physical configuration, what is the best analytical expression that would express the relationship between the pressure and the temperature and the density. So you can see that in some situations where we do not know the equation of state, this may be help. So let's look at sort of the various applications that so far have been used, and look at some of the properties that these techniques have been used for. And from the top, which is the most widely used and simpler to use techniques, to the bottom, which are the newest and yet still being developed techniques. But of course, the future is coming fast. So first, is replacing humans for tedious tasks. I was mentioning that thousands of analysts sitting in the basement of the Langley building at the CIA headquarters near Washington, and looking at images to try to find some terrorists or whatever, or looking for weapons facility and so forth. These can be replaced, so these people lose their jobs. So that's really something that is the main risk is in the job market. Once all these jobs are done by machines, then a lot of people will lose their job. But and there is, of course, the fact that the surveillance models pose a social issue, because you walk around and the government or some other entity can know what you are doing and your behavior. So that's a serious concern. But this is already not the future, it's the present. And then there is helping humans to understand what's going on by doing tasks that are tremendously large for a human to do. Like we can look at 10, 20, 100 objects, but when it gets to 1 million objects, even just counting that there is 1 million of them, it's a task that it will be very boring. And so that's similar to the previous application, but it's just a sheer size that it can help a researcher. And I will show you one example of this, where you have a lot of features. You just want to count them and and identify each one of them by its shape and size and features inside. And you just have to do this for many, many, many of them. And like I said, before it could be perfectly done by humans, but if you have 10 of them, then okay, you can ask graduate students to do it, but you wouldn't ask graduate students to do it for 300. And you certainly, so this is then helping the graduate student. It won't steal the job, but it helps him or her to get all the information and then process it, do the physics out of it. So that's a very important application, and I will show you one example. Then we are starting to get into the more front line, replacing physics-based models with neural networks, so that instead of doing a simulation, you do very many of them. At the end of the day, a neural network is like, in some sense, a glorified database interpolator. So you have a million simulations or 1,000 simulations or 10,000 simulations or whatever. And then you say, okay, this one is not so different from the others that I've done before. So instead of doing 1 million plus one simulation, you take the 1 million you already have done and interpolate from the closest. And I'm simplifying, of course. A neural network is more sophisticated than that, but that's the idea, that you run a bunch of them, you have them ready, and then when you want to do a real-time application, then you use this neural network to replace the simulation and give you what is a good answer. Of course, there is a question of how accurate it is, how stable it is, because if you go too far from the examples you have already done, it may give you a completely crazy answer. And so if you're doing this for important applications, like in our case, maybe space weather, but imagine medical application, okay, you want to be sure that the neural network doesn't produce junk. And one application of this, of course, is the forecasting, that instead of using forecasting based on physics-based methods, you can use this sort of extrapolation that a neural network can do to do forecasts. So you have all the previous times, and the neural network or some other, for example, graphical neural networks are used for doing that. You can generate the next steps using neural networks to give you what will be the next state of the system, given the fact that you already know that in the past it had all these other states. This is obviously a good case to do things like solar wind expansion or CMEs or other applications to the climate, where you are tracking the motion of a hurricane, for example. And then there is the fact of rapid decision. So however well this works, it's fast, and it's faster than humans. One example of this is in military applications, that you may have weapon systems that are on machine learning drive. So the machine learning decides to aim the weapon and fire at a given location at a given time. And there are situations where, for example, in tanks, where you have the soldiers not being able to respond fast enough. So they are working on methods that fire automatically. That's very scary because it may be wrong. So it bypasses the human decision. Another example of this is the fusion devices. There may be the need to trigger some response to avoid a disruption in a tokamak, and the response time has to be fast enough that you prevent the disruption that may damage the fusion reactor. And again, you may not have the time to have a human review the decision, and then the decision has to be made by the machine learning neural network. And then there is a true discovery. This is more of an open front. The machine learning, especially when it's unsupervised, may discover things we never thought about. For example, this has been used in some mathematical proofs, that some mathematical theorems could be proven by the machine learning tools in a way that had not been thought of by previous mathematicians. That's an example of this, that the machine discovers things that had so far not been let's say, come to the attention or to the realization of some scientists before, and so that you can make true discovery. And then finally, this equation discovery that I mentioned before is kind of a great possibility, because we are never confident that the machine is actually doing something right. You don't have a complete confidence. But if the machine gives you an equation, then you can play with that equation. You can try to understand why the equation has certain terms, what is the physical reasoning behind it, and also you can verify it. You can do the typical analysis of a data verification and analysis of the, testing, doing experiments to test whether the equation holds in certain condition. So that's kind of the ideal situation for a scientist. It's a tool that helps you find the equation, and then you can do your normal job of working with the equation. But instead of finding in a textbook, because Landau or Feynman or Einstein developed the equation, a machine has developed the equation, and now you are going to work on it. With a neural network, it gives the answer. You go, okay, that's the answer. What do I? So, a word of caution that all this may give you like a really crazy thing. Like, this is a friend of mine from Los Alamos posted on Facebook this picture where he asked machine learning. This was particularly the Adobe generative network that produces images. You would make a description of what you want, and it gives you a picture that represents the description. And he asked for a stellar-rated nuclear fusion rocket, and that's what the chat, well, no, this was not ChatGPT, but Adobe AI produces a completely crazy picture that doesn't have any physical meaning. So having said all that, I will now get into more of the business of actually showing you some examples that are taken from these two European projects and that I was the coordinator. One is just started, ASAP, the other one has just finished, that use artificial intelligence and machine learning to do a number of tasks for space science. So I'll give you a brief summary of what we did, and then I'll show you two examples if the time is available to ask you. Otherwise, we'll do just one. So ASAP has the goal of using machine learning in situ, in space. So deploying these techniques that have been developed in recent years to allow automatic robotic missions to have their own decision-making using artificial intelligence. That's an example of what I told you before that the military are doing, but this is not for military application, but it's just because the spacecraft has a delay from the time. I mean, if you're going on Mars mission or even to the moon, there is a time delay between the time on the mission and the time the information arrives on Earth. So there are situations where you want the mission to be able to do things on its own. In particular, these missions often have to decide what data to send. And right now it's done by what's so-called scientist in the loop. That is a person, usually rotating, that spends the day looking at the feed from the spacecraft. There is some quick data that arrives at low resolution, and decides, okay, this interval looks interesting, send down the detailed information about this interval. So this could be replaced by the mission deciding on its own that this is interesting, this is not, and what to send. That's an example. But when you're doing a robotic mission, you may decide, I'm going to go left, I'm going to go right, I'm going to go straight, or whatever, make a decision of what samples to do and so forth. And then, because it takes too much time especially if you go to other planets, then progressively become more time, and so it's not feasible to drive a rover on a very distant planet or a moon of Saturn or Jupiter. So this is going to be the future of space exploration, apart from the manned missions to the moon and Mars that hopefully will happen in the next years. But the rest will be robotic missions and automatic missions, so having more and more machine learning. The challenge there is the machine learning is extremely computing expensive and run on the fastest type of processors that we have on Earth, the GPUs. In space, the GPUs cannot be used because of the radiation. So you use much less powerful processors than the one that we can use on Earth. So this really gives you a challenge in making at least the most simple machine learning techniques work in space. And let's look at what type of techniques we have looked in the past that we can also deploy, we can try to deploy in space. So these are tools that, of course, do the data exchange. But it's this identification of extreme events where when you want the mission to send the data or go explore that particular situation. Or find lists of events of the same type and so forth. So tools that can replace the data of the mission with virtual data so that you can do the training of the neural network. So this is an example for the MMS mission and the cluster mission of replacing the scientist in the loop with the machine learning. And in this case, it looks like on the insight that later on, the machine learning is actually doing a better job than the scientist in the loop, who may be working at 3 in the morning and is not very sharp-minded at that moment and misses something, you know. And while the machine learning is always at its full mental capability. Then there are services that are for data analysis that I mentioned before. I can recognize where you are in space. So, for example, a spacecraft is in space doing its trajectory, and of course the space is evolving. So it may find itself in the solar wind, or in the magnetosheath, or in the tail, or whatever. And having the ability to automatically recognize the type of situation you are in. This is a classic application of the clustering techniques. But this can also be done with supervised learning, where you, for example, recognize features on the sun, and you can say, okay, this is an active region, this is not, this is an active region that is about to flare, this is not about to flare, and so forth. So these applications where the machine learning finds out what it's looking at. It's somewhat similar to what we were showing at the beginning of a Tesla car telling you, okay, we are running into a bicycle, and distinguishes a bicycle from a bus, or a bicycle from a tree, or whatever. And so this is the type of situation that you can often encounter in a space mission, or in even in a simulation that you want to say, where is the shock? And of course, there are various techniques to do that. Or the very big problem, where is the reconnection? What is the reconnection happening? And this is, again, something that the machine learning can learn to do. And then there is a forecast for space weather. Machine learning can be used in combination with physics-based or alone to predict things like a geomagnetic storm. This is an example of some work that we did in predicting the DST index based on data from L1 measurements. But there are many other applications that you can do for about, like right now we are actively working on the flaring and trying to recognize what active region is going to flare, and what is the class of flare that would be coming out of a certain active region. And that's a lot of people are working on that. But there are many other applications for space weather in the ionosphere, for example. I have some examples at the end, if we have time to get there, of a project to look at the ionosphere, the geomagnetic field, and the flaring. So the reason why we have to consider the machine learning is because of the challenge of doing the physics-based modeling. Physics-based modeling, you need to include all the physics, because a machine learning may learn from what you give it, but you're giving it real information, correct information. You can, for example, take the measurement of discover or ACE at L1, and the measurements done in this network of magnetograms or magnetic field measurements that are on the ground, that give the DST index, and you are feeding real information. And the machine learning will try to do the best that it can. But if you do a magnetospheric model and you don't put all the physics, the results may be worse than guessing. Some time ago, there was a published paper. Now maybe things have changed, but that sometimes it was better to do the Archimedes spiral than do an MHD simulation. So if you don't give the MHD simulation a good input, and you don't make the right boundary conditions, it may give you worse information than a machine learning tool that doesn't have any physics, but has been trained on real data. And the main challenge here, I'm mentioning in particular this new project that I have funded by the ERC called Terra Virtuale, where we're looking at the fact that modeling the magnetosphere has the challenge that if you don't include the electron physics, quantitatively, some of the answers that you are going to get are not correct. So this is an example for a magnetosphere. This is not the Earth, it's a smaller planet, it's a Mercury essentially. In this Terra Virtuale project, we plan to extend this to the Earth. But if you do a simulation with the electron physics, you get very different answer than if you get it with the electrons treated as a fluid, because you are missing important physics of the electrons. And so in that case, obviously, if you train a neural network on the good model that includes all the physics, then it's going to give you a better answer than if you use a hybrid model. Of course, the full kinetic model cannot be run in real time, not even close. It may take a month to do a few minutes of evolution of a magnetosphere. But you can train a neural network from those simulations to do other cases that you cannot afford to do in real time. And this is the reason why the kinetic models are required rather than the fluid models, and that's because it gives much sharper interfaces with much stronger energization. And then there is the issue of reconnection, that in fluid models is always approximated, while in full kinetic models is correct. And many of the triggering mechanisms in geomagnetic storms, in flaring, in CMEs, are related with reconnection. So if you don't get the reconnection right, the results may be off by time or give you a completely inaccurate answer. And again, machine learning can learn from kinetic simulation to put the right amount of reconnection in the right place at the right time, so that you can do then a fluid simulation, because of course you cannot do a kinetic simulation to do forecasting. Sorry, I need some water. And okay, so this is an example of the first example I'm going to give you. You see here is a simulation, full kinetic simulation, so it has all the physics. And in this yellow region is where a connection is happening. You see there are many of them all over the place. And there are many challenges. First of all is to identify them. And we have done some work to be able to use physics-based models or use machine learning models to identify where reconnection happens. But then there is the issue of, look at this. I mean, even just counting them, I'm sure if I do it 10 times, I get 10 different answers, because I don't see all the little yellow regions. I mean, here is a perspective. So the yellow regions are more or less of the same size, but those in the back are far away. So from the point of view where you see them smaller, but it's 3D visualization. So you have to go through this 3D information and look. I mean, this one is more elongated, this one is more elliptical, and this one is more spherical. And you can want to quantify that, and you say, what is the size range and what is the property within each one of these reconnection regions, so that then you can try to do some physical understanding out of them. And machine learning can do that for you, and that's what I'm going to show you next. This is a similar, but instead of the magnetic field lines, they show you the trajectory of electrons. Not trajectory of electrons, the streamlines of the electrons as a population. The actual electron trajectories are much more complicated, of course, because there is gyration. So you can imagine that an electron would gyrate around this mass. So in a situation like this, where you have, this is a magnetotail of the Earth, and you're seeing the outflow from one reconnection region in the magnetotail going towards the Earth to the left. It's very turbulent. There are many of these features, and you want to identify the properties of these features. And traditionally, this has been done with statistical methods. You say, well, what's spectrum of fluctuations in the Fourier transformation, or use a structure function, which gives a lot of information. Here, for example, it tells you at what scales the energy of the magnetic field drops down, at what rate. There is a Kolmogorov part of the inertial range, and then there is a dissipation range at the ion scale. This is data from the cluster mission, and this is simulation on the left that reproduces the data from the cluster mission. But this simulation took, as I remember, 45,000 processors, and it ran for 3 different blocks of 48 hours of CPU or work clock time. It took millions and millions of CPU hours. This certainly cannot be done in real time, and it's only a little part. We are looking at one recognition site. For the time needed for the front to go from the recognition site towards the Earth and travel a few Earth radii from the recognition sites towards the inner magnetosphere, the ring current. So that's tremendously expensive, and machine learning can obviously do that. So now we want to identify all these different features that you have seen in the previous simulations using the clustering techniques. And you have seen the picture. So certainly we are not interested in situations like this, or we're interested in identifying distinct features like this, these elongated shapes. And dbScan seem to be the best compromise, because you see it's extremely inexpensive. It takes 1/100th of a second to do the analysis of one of these images, and it is accurately distinguishing the different features. I see that some of the others miss and misinterpret the distinction. We count this as one cluster and one other cluster, another cluster, which is certainly not what we want. Typically, the spectral clustering tends to be really the best, but the spectral clustering is awfully expensive. And for the same that this took 1/100th of a second, this 0.39 seconds, and it's very memory intensive. So often it doesn't fit on a memory of one core. So we gave up on the spectral clustering because it seemed to be, let's say, it needs further development for it to be practically usable. But the dbScan is very well developed. And so this is the result of dbScan applied to this recognition. On the left, it is the Earth side part of the recognition, and the tailward side on the other side. And you see that there are many features here. It identifies each cluster, and you see from above. So it's very many distinct clusters. Now you can go into each one of these clusters and ask what are the local features there. So you're no longer thinking about structure function and K spectrum. You are looking at every individual feature of the turbulence system. There are many vortices in a turbulence system, many features, many current features within a reconnection region, within a turbulent domain, sorry. And in 2D, it's easier, but in 3D, it's very hard to go identify all of them. And the question is, for example, you have different current layers of different sizes. Is recognition more likely to happen in certain of them than others? Or is electron scale recognition more happening more at small scales, as of course one would imagine, and ion on large scale? So, but you want to quantify that by actually looking at every single one of them and looking at the properties of every single one of them and let the machine do that. So this is an example of the application of the dbScan to this turbulent system generated by reconnection in the magnetotail. And you see that it has identified, I remember in this case, 244 features. And then it's going to look at every one of them and look at E-parallel or other indicators of interest in physics going on. E-parallel is typically present during reconnection. So you see that reconnection cases, or say large values of E-parallel, tend to be in small scale features. So these clusters that are approximated with an ellipsoid, and you can then look at their size, of course, the largest axis, and the ratio between the largest and smallest axis gives you the elongation. And so often you would imagine that recognition is going to be more likely happening when it's elongated. But it may actually be that when it's elongated, the recognition has not yet happened, and it will happen later. So these clustering techniques allow you to investigate every single one of these features and see their evolution and understand the physics that is happening at every scale. So that's different from the statistical approach to turbulence. The machine can actually look at turbulence as a very complex system with many, many features on many, many different scales and go look at every one of them. So this is an example of agyrotropy, which is another feature that is typical of reconnection. And you can see here that, again, agyrotropy tends to be largest at the smallest case, but in this case also tends to be largest at the highly elongated features. When a feature is, like the current feature, is highly elongated, so it's a long current sheet, it tends to reconnect. And the agyrotropy shows you that. And you can quantify, this in a quantitative way by looking at the size of every one of them and their elongation, and then within that, the agyrotropy. The agyrotropy, by the way, is let's say, asymmetry of the pressure tensor in the plane perpendicular to the magnetic field. So pressure tensor is anisotropic when not the temperatures are not the same in every direction, but it's agyrotropic when the two components of the temperature perpendicular to the magnetic field are not the same. That's a famous indication of recognition. Energy exchange, the same. You can ask, where is the energy exchange the most? In small scales or large scales, and you can see here again, it's mostly at small scales. And then you can ask the question, is this recognition happening involving the ions only, the electrons only, or both? And here from this picture, you can see that the agyrotropy is largest when the electron current is largest, and the ion current is only negligible. So this tells you that within a turbulent system, most of the recognition is happening at the electron scale. That's another reason for saying that if you don't resolve the electrons, you're not going to get the physics right, because the recognition dissipation is going to happen at the small electron scale, not the large ion scale. It happens on the large ion scale if you don't resolve the electrons. Once you resolve the electrons, you find that the turbulence brings down the importance of recognition only at the small electron scales. And this is something that machine learning has told us by analyzing a turbulent system and showing that it's the smallest features at the electron scale where the electron current dominates. So the electrons are moving and the ions are nearly not moving. That recognition happens. Now there is not so much time, so maybe I'll skip the second example that I briefly mentioned, is the analysis of distribution function from the MMS mission. The distribution function have these complex features that you see in this picture. And you see that is a three-dimensional object that you have to look at, Vx, Vy, Vz, or V parallel, V perpendicular 1, V perpendicular 2. And within this, you may identify specific features like a crescent. That was a big discovery of the MMS mission. Or you can find that there are different beams. Especially for the ions, the beams are very complicated. This is an ion distribution. You see that there is at least 1, 2, 3, 4, 5, 6, but then it starts to become, do we consider these two different beams, or is it the same? Or this is like 3 beams, or is like 2, or what? Or is it 1 with complicated structure? So you see that you have to come up with some strategy to do that. And one way to do this is the Gaussian mixture model, which is another clustering technique that, let me see, I just briefly mentioned, that automatically detects, the different beams within a distribution. But I don't have the time to go over this one, so I'm inviting you to read the paper that is mentioned here, and there is a new one coming, where we show how you can use this technique to identify the number of beams or the complexity of the distribution function. And this is actually something that we want to deploy in space missions, so that the space mission realizes, oh, I'm in a region where the ion distribution is very complex or the electron distribution is very complex. So I'm going to take the data here and transmit it back to Earth. But let's skip that one. And just briefly mention the application, because I want to leave some time for questions, so I imagine that I want to finish about now. The applications of space weather, since I think you are more in that business. This is a new project funded by the Belgian military for telecommunication. As you know, the military are particularly affected by disruptions of telecommunications. There is a famous event that happened during the Afghan war, where there was a unit of the Marines that were operating in a remote location, and they wanted to ask for aerial support, so they wanted to have an airstrike against the enemy, and the communications were not working, so many of the soldiers were killed. So this is why the military wants to be able to predict when there is going to be a blackout in telecommunications. And that comes because of the flares, because of disturbances in the ionosphere, gives you problems with the GPS. So we are working on, we are working on providing the Belgian military, actually, then the military will share it with NATO, with the other countries in NATO, these tools to predict geomagnetic storms, making prediction of the geomagnetic field, ionospheric disturbances, and flaring. And with this, I close and invite questions if there are any.
Are there questions? I will probably repeat them because I don't think Giovanni will be able to hear you, but if you have any questions. Yes, please.
Would be curious to know, first of all, thank you for the very insightful talk. I'm curious about the uncertainty quantification part of this class. What do you think could be a promising technique to quantify uncertainties of these models, especially considering that this could be a potentially high-risk setting to deployment?
Okay, Giovanni, I suppose you not here, right? So the question is, at the beginning of your presentation, you discussed a bit the issue of the uncertainties that are sometimes difficult to quantify. So the question was if you have any idea how this problem might be tackled to somehow put some number on the uncertainty of some of these models.
That's very true. That's especially discussed for the case of ITER that I'm aware of. For ITER, then you want to have a confidence level, or whether the machine is giving you a good prediction that the disruption is happening, because you don't want to have false positives, in the sense that you don't want to close down a shot in ITER because it gives you a false alarm, but also you don't want to miss cases where you have a prediction that the flare is not happening, and in fact, the disruption is happening when in fact it's not happening. And you see the analogy there with the flaring and with other applications, which is so for that there are techniques that people are developing. In particular, what is called the explainable AI. So the machine learning tools tells you not only that a certain thing is going to happen, but it tells you why it thinks is going to happen. For example, in the case of ITER, there are many channels of data that you're going to digest to make a prediction that the disruption is going to happen. And the machine can tell you what is the weight of the different channels, and then you can identify that it's a reasonable guess, because it's actually using information that is relevant. If you think it's not so relevant, but again, you may not have the time in the case of ITER to make this decision, because a human cannot revise So it has to be automatic. But you can you can design protocols to make the decision making of the whether or not to stop a shot on ether based on the information you have from the machine learning. But these explainable AIs give you not only the method, I mean the answer, but the reason for the answer, and that's one. Now, for the machine learning tools that replace physics-based modeling, you can define error bars and have information about what is the prediction and what is the error bar on the prediction. So there are machine learning tools that do that as well. So depending on the application, you may want to have different ways to quantify the uncertainty. But I think in machine learning at this point, there is a fundamental distrust that, it's not so much to attach a number as it may be completely wrong. When you're predicting a flare, for example, the really big flares, which you care about, are easier to get a good prediction. But for the smaller flares, it's sometimes difficult to be sure that it's a certain class rather than another. So quantification of the error is also something that many of the techniques actually provide. It doesn't just provide one answer, but it provides an error bar. One example of that is the variational autoencoders, for example, that the variational autoencoders assign to the latent space not only the value of the latent space, but the sigma around the value. So with that, you have statistical information about how accurate the determination is. So there are many ways. It is more of a cultural barrier. It's not that the machine learning cannot be trusted because we don't know the uncertainty. It's that we don't trust it because it's a Frankenstein effect. It's a new thing, and we don't want to put our lives in the hands of a machine.
Okay, so there is another question, Giovanni, it's concerning specifically the three things that are mentioned now on the slide that is currently being shown. It's a question from Sean, whether you have any recent actual improvements in forecasting any of these three, because as he says, this has been, people have been trying to forecast any of these three type of phenomena already for a long time. Yeah, so
there are always new developments. So if you look at the literature, we are just starting here, so we don't have yet actual very much in terms of results because it's a new project. But if you follow the literature, this has improved. And one way you can improve this is, of course, to get more data. So, for example, for the flare forecasting, there has been a focus on using HMI, so the magnetograms, but you can include also other wavelengths, as you see there in the picture, different wavelengths, and digesting the information from multiple lines can give you better predictions. And there have been papers where they show that as you go from using only HMI to also including extreme ultraviolet, you improve the prediction. So it's machine learning. It's a train that cannot be stopped. Yeah, the performance will keep improving because people will get smarter and smarter techniques and more data. But the crucial thing is more and more data. And as we get more data, we're going to get more and more predictions. So it's just the effort of actually doing it. But there are so many groups around the world that are doing it that the progress is fast. Of course, we are at the beginning. So right now the predictions are not yet, perfect, but they are getting better. This is actually very true for tokamaks as well. There has been a constant improvement on this because this has to be ready when ITER will operate, because otherwise you cannot risk. If there is a disruption in ITER, you have to stop if it damages significantly the machine. You have to stop the machine for a couple of years to do the repairs, because you have to use robots. Everything is radioactive, so that's it has to work by then. So they are working hard on that. But the same is true in every week. I would say I see a new paper coming out on flare prediction, and there is constant improvement.
Another question from Luca. We still have 2 minutes.
Of course, the simulation prediction. But I mean,
our eyes will shake our legs.
Sorry, something came up. Okay, I'm back.
Okay, so question from Luca, specifically regarding the scintillation forecasting. If you have any specific application in mind, and if so, which one are you mainly targeting, and what are the
It's military.
forecast horizons that you...
It's a military application, so it won't be public. It's going to remain. It will be shared with other militaries in NATO, but it's not going to be shared with the public now. The military don't like to share.
Okay, one more final question.
Yes, thank you, Gianni, very much for the lecture. I was wondering if you are going to be doing this forecasting, how are you going to deal with the really strong events where you simply do not have enough data?
Okay, yeah, this was a question that I was also thinking about, but this was Michaela asking it, which is the question that for the extreme events, of course, there will always be very little data available. And so the question is, if you have only a few of the very extreme events, how can you ever train your models to handle
Yes,
this?
so that's a very good question. So there are a number of techniques that have been used in the past where you generate fake extreme events based on the one that you have. And so that you upgrade the number of, you have to, of course, to train with a balanced set. So you reduce some of the very frequent events like no flaring or very weak flaring. You take a subsample of that, and then you oversample the distribution by generating data that there are machine learning techniques to generate new data from the existing data set that you have, and that's where the generative neural networks can help. But there are simpler techniques that take input parameters from different, let's say, X flares, and generate new ones. But that's also work in progress because that can be continuously improved. But that's one of the reasons why in astrophysics it's so important to use generative neural networks, because you can generate events that are very rare, and you can generate them. And then you can use simulations as well. Huh? So one example that can also be thought about is that, for example, for these extreme events like Carrington event, or even the ones that are even stronger than the Carrington events, you could use simulations to generate, synthetic data sets that can be used to train the neural network. So there are various techniques. Some are physics-based, some are statistical, some of these generative neural networks, and they all can increase the number of training sets that are coming from extreme events.
Okay. Any final short questions or comments or remarks from anyone? No? Okay.
All right.
Thank you, Giovanni.
Thank you. Thank you for the invitation. Sorry I couldn't be there in person.
No problem. Take care of yourself.
Okay. Bye, everybody. Thank you.